Hello, welcome to this video on chiral catalysis. Before we look at that, we have to look at drug action. And what is drug action? Well, we have an enzyme, and in the enzyme we have an active pocket, and there are groups in the active pocket that are going to bond to the um, some sort of a ligand that's going to go into the active pocket. Okay, now the active pocket will affect the action of the enzyme. Into the active pocket from our bodies normally goes something called an endogenous ligand, and the endogenous ligand will um, form some sort of action from the enzyme. That's the normal case. Okay. Now, what we have now is a drug, and a drug will mimic the endogenous ligand. Okay. Um, and it will presumably perform the same effect as the endogenous ligand, and that's called an exogenous ligand. The drug is the exogenous ligand. Okay, now we have two drugs here, and I'm circling the chiral centers there. Um, on the left we have drug A, and on the right we have drug B, and they're optical isomers of each other. Okay, as I say, on the left is drug A, and on the right is drug B, and they're going to go into the active pocket. Now, if drug A goes into the active pocket, let me show you what happens. It will match up precisely with the groups already in the active pocket, and it will bond nicely to the active pocket. Okay, so drug A looks like a good candidate for the drug, but it's optical isomer B matches, but C and A don't match. So optical isomer B isn't a good match. So only one of the chiral compounds, or the chiral drug compounds, will fit nicely into the active pockets and will bond and will have an action on the enzyme. The other one won't. Okay, so when we're making drugs at the moment, normally we make them as a 50-50 mixture. This is known as a racemic mixture. Okay, now that means it has 50% of one molecule and 50% of the other, but only half of the drug therefore works. And now this is a waste of the other half. Okay, so we're wasting raw materials, and the other half can cause safety problems because it can have what's called side effects, and we don't want that. Okay, so we only want one optical isomer. Okay, and we want to eliminate the wasted one that does nothing, does not work in the active pocket. And as I say, we do this for two reasons: for wastage reasons, for economy, and for safety. Okay, and that's why we use chiral catalysts, because it enables us to make one isomer over the other. Okay, so how do we? Let's pretend we're making a chiral molecule here. I'm going to use as an example um, the addition of HCN to ethanol. Okay, because this produces a chiral molecule. All right, and there's my ethanol. There it is. Okay, now the CO double bond bit in the middle is planar, as you know. Okay, so because it's sp2 hybridized, and because of that, the original attacking molecule, the the CN minus ion, can attack from either the top or the bottom. Okay, there it can attack from the top or the bottom, and the attack is 50% either way because it's planar. Okay, so it can attack from the top, and if it attacks from the top, we get this molecule. There's the OH and there's the H part. All right, and that's from attacking from the top. We get that enantiomer, that optical isomer. And if it attacks from the bottom, we get something like this, sort of the mirror image of the thing at the top. Okay, so we'll get that. It's the enantiomer. Okay, now we should get these two as a 50-50 mixture. Why is that? Because it attacks from a planar position, and it's just as likely to go from the top as the bottom. And a 50-50 mixture is known as a racemic mixture. Okay, so if we attack from the top, we get 50% likelihood, and we attack from the bottom, we get 50% likelihood. So we get a 50-50 mixture. Now, these two optical isomers that I've made here, the special word for that, they called it enantiomers, and we get two enantiomers. They're just optically active isomers. Okay, so if these were drugs, half of them wouldn't work. Okay, only one of them works. So half of the drug would be useless. Okay, so what we do is we try and make only one enantiomer. and we only want the correct ones for drug action. Okay, so let's do this again. Okay, and how do we do this? We use a chiral catalyst. All right, now these sound strange, but they're not so hard at all. I'm going to use the same example here, and I'm going to use ethanol again. Okay, you wouldn't use ethanol, but this is just an example. So using the same example, there's my ethanol molecule. All right, and now first of all, I change one of the groups. Okay, this is my starting material, ethanol, and I'm going to change the hydrogen at the bottom. And I'm not going to say how we do this, but we just change it. Okay, so we have our ethanol molecule, and instead of the hydrogen, we replace it with something big. Okay, a big thing that prevents attack from the bottom. Okay, now this is still planar. Okay, but now because of this big group, it will bend over, and the Cn minus ion is less likely to attack from the bottom now. So it's more likely to attack from the top, and I've given the example 90% from the top and 10% from the bottom. And the big group prevents attack from the bottom. Okay, so what happens then? If we have this, we're going to get a molecule like this. Okay, oops, I've done that wrong. Let me do that again. Okay, let me get rid of that. Okay, so we're gonna if it attacks from the top, let's pretend it only attacks from the top, and there we go. So the Cn goes from the top, and we get our CH3, we get our OH, not like that. We get an OH like that, and we get our big group there, don't we? All right. Now what we do now is we use some chemistry and we remove the big group. Okay, and we end up with only one chiral molecule, and there it is. Okay, so if we've done it properly, we get 100% or 90% of only one enantiomer. Okay, because we've prevented things from happening. We've prevented the CN in this case from going from the bottom. Okay, so you add a group, you perform the reaction, all right, and you only get one enantiomer, then you remove the group. That's why it's known as a catalyst, because you only end up with one enantiomer, and that's the one we want. Okay.